Welcome back to Series on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, and also the next, we're going to do examples of another comparison test called the limit comparison test. Now again, to distinguish this one from the other comparison test, it's called the limit comparison test, which means that in order to evaluate whether or not the series converges or diverges, we're going to have to take a limit. All right, so let's first look at our series here and then talk about how we actually do that. We have the series from n equals 0 to infinity of 1 over 3 to the n minus n. All right, and we have an a sub n, as we have seen in some other previous series tests. Our a sub n is really just the argument of the series at hand, which is 1 over 3 to the n minus n. And we also have a b sub n. And this b sub n is to the limit comparison test exactly what it was in the direct comparison test. You basically pick a b sub n that's very similar to the a sub n, but if you were to write it as a series, it would be very easy to evaluate whether or not it converges or diverges. And generally, the b sub n is either going to be a p-series or a geometric series or something like that, or even a harmonic series. And in this case, we have in the denominator 3 to the n minus n, so the easy choice is to remove the minus n, so our b sub n is just 1 over 3 to the n power. And also bear in mind, if we were to write this b sub n as a series, such as the series from n equals 0 to infinity of 1 over 3 to the n, it would actually be a convergent geometric series. Alright, so how do we do the limit comparison test? In each case, what you do is you take the limit as n goes to infinity of the quotient of a sub n and b sub n. And you find out what the answer is, okay, obviously. And the first criteria is the kind of the most confusing. It's if the limit is greater than 0, so like 1, 2, 3, some finite number greater than 0. Then you look at what b sub n does. So if you looked at the series of b sub n and it converged, then the series of a sub n, your original series, also converges. If your b sub n, if that series diverged, then the original series also diverges. So basically, if the limit is greater than 0, your series just follows whatever b sub n would do. Okay? If the limit is exactly equal to 0, then your original series automatically converges. And then if the limit goes to infinity, the series automatically diverges. So the only one you really have to think about is really just the first criteria. Okay? So what we're going to do is we're going to compute the limit. And it's going to be the limit as n goes to infinity of our a sub n, which we just determined. That's just the argument of our original series, divided by b sub n 1 over 3 to the n power. All right, so let's actually compute this limit. Now, we can actually put this in a much easier form to work with. We can actually rewrite it as the limit as n goes to infinity of 3 to the n divided by the quantity 3 to the n minus n. All right, now, if we were to simply plug in infinity here, we would have infinity over infinity, which is indeterminate form. So this is a perfect opportunity to use L'Hopital's rule, in which case we take the derivative of the numerator with respect to n here, and divide by the denominator with respect to n, okay, the derivative that is. So if we differentiate 3 to the n, that gives us 3 to the n times the natural log of 3. If we differentiate the denominator with respect to n, 3 to the n is 3 to the n times the natural log of 3, and the derivative of negative n is minus 1. All right? Now, we have all these constant terms, but we still have a 3 to the n over 3 to the n, so to speak. And so we still have indeterminate form, since we have a limit as n goes to infinity. So let's use L'Hopital's rule a second time. So we're going to differentiate the numerator with respect to n, and also differentiate the denominator with respect to n. All right? So when we do that, what happens? Well, we already have 3 to the n times natural log of 3, so when we differentiate it, we get an extra natural log of 3 there. Still have a 3 to the n. When we do this to the denominator, the same thing, and then minus 1, that derivative is 0. So, in other words, we have 3 to the n times the natural log of 3 squared divided by 3 to the n times the natural log of 3 squared, and that's the limit as n goes to infinity. But notice, we have a natural log of 3 quantity squared in both the numerator and the denominator, so those terms cancel. And then we have a 3 to the n in both the numerator and denominator, so those cancel. So there's no need for the limit anymore, it's just 1, because everything cancels out. So our limit is 1. Well,
This limit is not 0. It's not infinite. It's greater than 0. So we're going to obey the first criterion here. The series follows whatever b sub n does. So if we were to write b sub n as a series from n equals 0 to infinity of 1 over 3 to the n power, this would be a convergent geometric series, right? Because we'd have 1/3 to the n power. Our common ratio is less than 1. So b sub n as a series is a convergent geometric series. So because b sub n converges, our original series also converges. And I guarantee you, if you evaluated the convergence or divergence of this limit using the direct comparison test, which you could also do, you would get exactly the same result. And a lot of times the limit comparison test and direct comparison test can be used for the same problem. It turns out that in some cases one of them might be easier than the other. All right? So, hopefully this video gave you an intuition on how to conduct the limit comparison test. This is one example. In the next video, we're going to do another example of the limit comparison test, so please join us there. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.